Okay, so why don't we get started? I'm going to start. All right, so I presume you all turned in lab 2 and you need to take a moment and recover. Lab 3, which I was supposed to put up on Monday, I delayed putting it up. I did post it before this coming to class. It's due in 3 weeks, so you have plenty of time, but don't waste until the, wait until the last minute and waste time because you will again get into a time crunch. Okay? There's also a homework out, which was supposed to come out also last week. I held off to give you more time to work on the lab. Okay, so we are getting a little delayed, so things are getting more compressed because I have tried to be more flexible in terms of deadlines, but we will have to still get all of that work done. All right, so homework 4 is out, lab 3 is out. I had cancelled a makeup class last Friday. If you remember, there was a makeup lecture last Friday which I cancelled because of the lab and my own scheduling conflicts. I will instead have it this Friday. Okay, 4 p.m. this classroom. Don't come at 2:30. There's a different class at 2:30. Okay, come at 4. All right, so we will continue the discussion from last time. We were talking about consistency models. Today we are going to switch gears and talk about more about implementation. Okay, so and this is just a tiny peek into the implementation, because when we get to World Wide Web next week, in fact a week from today, next Wednesday, we are going to get into a lot more detail about what web does and so on in terms of caching and consistency. But for now, we are going to look at two different models. One is called the primary based model, the other is called replicated write model. Okay? In the primary based model, you have, so remember we are talking about data replication still, okay, and consistency and so on. So in the primary based model, there is a primary node that's responsible for the data item. There's a primary replica and there are secondary replicas. Okay. Writes actually have to go to the primary replica, which is then going to somehow send it to the secondary replicas. Okay, and then reads can happen anywhere. That's the general assumption. Okay, so writes go through the primary, reads can occur at any replica. So that's called the primary based protocols for data replication. Replicated write protocols, which we will also see today, don't make any assumption about the primary. Okay. There is, all replicas are equal. There is no primary and secondary. So what that means is each write request, if you open a file and you write to it and it's replicated, when you save that file write has or save has to be sent to multiple replicas by your client, rather than being sent to only one primary and it's sending it to the secondary. Okay. So no primary is assumed. You can take writes can take place at any replicas or multiple replicas, as we will see as well. And then you have to somehow deal with all of those issues. Okay, so let me start with the first one. This is called the remote write protocol. Okay, and essentially in this case, there are multiple replicas here. You will see that there is a client, and then this is the primary replica that holds the data item X. Okay, and there is some backup server which we'll get to. Now there are lots of arrows here, but all that the arrows will tell you, if you will see carefully, is when a write request comes in, that write request W1 is forwarded to the primary and an acknowledgement goes back. That's all it's saying. Okay. When a read request comes in, okay, it is also going to go to the primary if it's not replicated on their disk, and a response goes back. That's all it is saying, really. Okay. Now you have here additional messages that are going back and forth that essentially allow this write to propagate, because it has gone to the primary now. That has to propagate to multiple nodes, and that is what the additional arrows do. So you will see that the write request came in, it went to the primary. Now the primary is actually sending this W3 message to this node, that node, and that node, which are all replicas. So it has, so the write came to the primary, it sent it to 3 other nodes, so that your write request has reached all the 4 machines that are shown in that case. Okay. So you will see this W3 request, because the write comes here, and then the write is forwarded to the primary, which is this machine, and then it sends that write saying here is a new write, he has a new write and he has a new write to all of those three machines through your W3 message. And then the acknowledgements, the W4 are the acknowledgement messages that come back saying those machines have received the write. Okay. Now in this case, reads are local. You will see that because all the machines actually have a copy of the data item. When the client reads it, this machine is supposed to have it, so it just returns the data item. Okay, so writes go to the primary, they get propagated, reads are local. Okay, very simple idea. Any questions about this? Okay, now there is some additional things here which says this protocol that is shown here actually implements sequential consistency that we talked about last time. Okay, it allows you to have a sequential ordering of writes that everyone agrees to, program order is preserved and so on. Okay, that's an aside, but basically it just allows you to propagate your writes. Okay. Now here is a different protocol that says let's try to make the writes local. Those were remote writes where the primary was remote to where the client was actually updating the machine, updating the data item. In a local write protocol, what happens is when a client starts writing to a file or a data item, okay, the local node essentially becomes the primary. Okay, the role of the primary can move across machines because there are k replicas. Okay, one of them has to be designated as the primary. You can pick that statically, in which case all writes have to be sent to that node, or you can pick that primary node dynamically, depending on where the write is occurring. So here is a scenario that actually shows you this. Okay, so this machine here is still, or this disk here is still the primary node, but the client opens the file and starts writing to it, and the client is local to that machine. So that causes the responsibility of the primary to shift from this node to this node. Okay. So now that machine has become the primary, so all the writes can actually occur there and directly get propagated elsewhere rather than first being sent to a remote server and then the remote server propagating it. Okay, this is why it's called a local write protocol. Okay. When we talk about network file system or NFS in a couple of classes, you will see both of those techniques actually are present in NFS. Okay, in one case there's an NFS server, so NFS clients will send all the writes to the NFS server, and the NFS server can notify caches or other NFS replicas. And we'll see in new versions of NFS, such as NFS version 4, a client can become a temporary server for a file. The file can actually be delegated by the server saying, you deal with it. You are the temporary server for this file, not for all files. And then all the file writes at that point are local, which means they will get better performance. They don't have to be sent to a remote machine. Okay? So this is called a local write protocol. Okay? Now the same thing happens in this case. This machine has taken over, it's the new primary for data item X, it becomes a write. So when a write comes in, it basically is going to send that write to all of the other machines, okay, and then all the other machines are going to send an acknowledgement. Same thing as before, because the write still has to be propagated to other machines, but the current machine is actually the primary. Yes? Okay. Okay. So question is why do you say move X to that other machine? This is where that other machine takes over the job of becoming the primary for the machine. So it holds the primary copy of that file. Okay. So question is the file actually sent over. So initially let's assume that there is only one copy, or maybe it's not replicated, or this is the primary or the master copy of the file. Okay, maybe the other copies may not be up to date. Doesn't matter what the scenario is. So when the file is opened for writing on this machine becomes the primary. Now it has to take over the responsibility of being the primary. If it already has an up-to-date version of the file, you don't really have to send it over. That's the worst case where it did not even have it. Okay. Okay. So now that's basically this complicated looking example is not really that complicated. All that's happening is client writes to a file. This is the primary. It has already taken over as the primary. That write is sent to all the replicas. All the replicas send acknowledgement. That's all those messages essentially do that. And then when a read request comes here, that's also local because the file is replicated and every machine has an up-to-date version of the file. Okay, it's keeping it consistent by propagating all the writes to all the machines. Okay. Okay. So now, so those were very simple protocols where you had one primary machine. Okay, there was a primary copy of the file. Now we will look at a different technique which is called replicated write protocols. Okay. In this case, we will relax the assumption that there is a primary at all. There are no primaries anymore. Okay, you have a set of machines that all have a copy of the file. Okay. Now when you write to that file, somehow you have to write to multiple machines to keep it consistent. Okay. Ideally you could write to all the replicas, that's fine. Okay. But we will see that there are techniques that allow you to write to a subset of the replicas and yet ensure correctness, which means you will never get out of date version of the file. Okay. And it's advantageous to not have a requirement that says you have to always write to all the replicas, because some replicas may be down. Okay, you will not be able to make progress if you say every update has to be propagated to all the replicas and they actually have to acknowledge before I can make progress. Okay, so here is a scenario where you can write to a subset of the nodes and yet get correctness guarantees. And these protocols, okay, are called quorum-based protocols. If you ever heard of the term quorum in a distributed system, here is actually a scenario where we will see what a quorum means. You probably heard the term quorum. It essentially means that you have to have some number that is some sort of a majority in some sense. Okay? And so here is how the quorum-based protocol works. It's going to be a voting-based scheme. Okay? We will assume that a file has a version number. Okay? Every time you update a file or you save the file, the version number is incremented. Okay? The highest version number of a particular file across the system is the most up to date. Okay. Ideally, you want every replica to have the file with the highest have the highest version number of the file. Okay. But we will relax that scheme and see that some replicas may be behind. They may not have caught up. They may have an outdated version, which means they have a version number that is not the maximum. Some other replica actually has a more recent version, and that's okay because we'll see how to deal with that. Okay. So assume that files have version number that get incremented upon every write. So we are going to essentially use voting to figure out how this is going to work. Okay. And the voting is going to work as follows. We will assume that the file is replicated, and we'll have two kinds of quorums, a read quorum and a write quorum. Okay. A read quorum says that to read a file, let's say the read quorum is n subscript r. To read a file, you have to contact that many servers. All of those servers will tell you the version number of the file that they have. If the version numbers all match exactly, you go ahead and read the file. Okay, that's the basic idea. To write a file, you got to send that file to the write quorum, which is NW servers. Okay, NW and NR are two parameters that we are going to set in just a moment. So the rule for writing is you have to write to NW servers, and so all of them now have the most up-to-date version of the file. Okay, is that clear what I just said? To read a file, you have to contact NR servers. If those NR servers all will compare their version number and the version number matches, you can read the file because they all agree and they voted on the file version, which is what is the version we have. The vote agreed 100% among the read quorum, and you go ahead and read them. To write the file, you have to write to that many servers. Okay? And the rule to pick NR and NW is what is shown here, which says the write quorum has to be a strict majority. Okay, you can pick, if there are n servers, there are many ways to pick what the write quorum is, but it at least should be a majority. It has to be strictly greater than half the number of servers in your system. Okay? And the read, once you pick your write quorum, the read quorum should be chosen such that NR plus NW is also strictly greater than n, which is the total number of servers. Okay? And I'll give you an example to show how this works. There will be 3 different examples. These are all taken from the book. This has 12 servers, okay, A through L. Each of these letters represents a server, and we'll talk about only one file just for the moment. Okay. They all have a copy of the file. The file has a version number. Every time you write to the file, the version number is incremented. Okay. So there are 3 different scenarios of how that protocol is configured. Here it says read quorum is 3, write quorum is 10. Okay. So what does that mean? It means if you're writing to the file, you have to pick 10 out of those 12 servers at random. Doesn't matter which 10 you pick. Pick any 10 servers, send the write to those servers. Now those 10 servers have a most up-to-date version of the file. Okay? To read the file, you can again pick any 3 servers at random. Okay? If those 3 servers agree on the version number, then you are guaranteed that that's the most up-to-date version of the file. If they disagree, then you repeat. You pick another 3 servers at random until you get them to all agree. Okay? So what is shown in this picture, the first picture here, the dotted line tells you the write quorum that was chosen for the most recent write. Okay? 10 servers were chosen. So you will see that there are 10 servers. A and B were not chosen in that write quorum. So everyone but A and B actually has the most up-to-date version of the file. Okay? Now, yes, you have a question there?
When you select 10 servers for write, do you check whether all of them have the same file updates?
Okay, the question is when you pick the write quorum 10 server, do you pick whether they have the same update? In this case, we are assuming that you are going to save the whole file. So it doesn't matter what they had before, now they have the most up-to-date one. If you are updating a part of the file, what you are saying makes sense, the rest of the file better be up-to-date. But let's just say that you open your editor, you make some changes, you hit save, the entire file is saved to disk. Okay? So now you just pick 10 servers and send that file to those 10 servers. So what they had before doesn't matter anymore. Okay? All right. So now you pick, to read, you have to pick 3. That's our rule. Okay? So in this case, you picked A, B, and C. Okay, A and B did not see the write. C did see the write. So C's version number is going to differ from A and B's version number. Okay, the version numbers won't match. The read is going to fail internally, not externally. It will fail internally. System will retry. Okay, you will pick 3 other servers. Okay, so long as you pick any 3 servers that does not include A or B, you are good. Until then, you will keep failing, and then maybe you pick I, J, and K at some point, let's say. In that case, they will all have the same version number. That's guaranteed now that the version number is accurate and most up to date. Okay, then the read can simply returns with that file. Okay, so you have to ask, why does it guarantee that if you pick your read quorum this way, that you will actually, and all those servers agree, why does it tell you that you will actually get the most up to date version of the file? Yes? Yes. So the point that is exactly being made is the way we have chosen a read quorum and write quorum guarantees that in your read quorum there will be at least 1 server from the write quorum. That's what we essentially did. That is why we said NR plus NW has to be greater than N. Okay. Furthermore, this has to be greater than half. Okay. And I'll show you an example what happens if you don't pick half. Okay. You might actually end up with a problem. Okay, so in this case, majority of the servers see the writes. Okay, your read quorum is chosen so that there is absolutely no way you can pick NR servers which does not include 1 server from the write quorum. So in this case, because you have to pick 3, there's no way to pick 3 where none of those 3 have seen the most recent write. Because you pick 10 out of 12 that's already seen that write. So there's no way to pick 3 more where you can only pick 2 more that have not seen the write. The third one will have always seen the write. So there is no way for the read to succeed and give you an outdated version of the file. Okay, the read is either going to fail, or if it succeeds, you are guaranteed it gives you the most recent version. Does that make sense? Yes?
So when the files do commit to all these servers, do they commit instantly at one time and on the different machines are like?
Yeah, the question is, does the files when you commit, do you actually send them all at once? You can, that is an implementation detail, but obviously you have to do it in a way where they all actually acknowledge and then they commit or something like that. Right? Otherwise, if they commit at slightly different times, you might have a read where it's reads and writes are concurrent, you might have problems. So we'll have to deal with that separately. Okay, right now conceptually, let's assume it's instantaneous. Okay, all right. So here's another example. We picked a different way. So here the read quorum is 6, the write quorum is 7. Okay, the dotted line includes the read servers, which are essentially these servers, and the solid block shows you the read quorum. Okay, so in this case, you will see that this read quorum won't succeed because H has seen the more recent version of the file. A, B, C, E, F, G have not seen that. Okay, so G is going to, not G, H is going to differ from the other 6. So the read does not succeed. Okay, but you will see that there is no way to pick 7 servers where the read will ever succeed at all. The read will always fail in this case, because no matter how you pick 7 servers, there will be one server that is actually not in one of those 2 core. Okay? So you designed a system where you can always write but never read. Okay? Not a very useful system. The reason that has actually happened is we violated our rule. Okay? The rule said that the write quorum has to be strict majority. We actually set it to half, not greater than 6, which is why we have that problem. Okay? So it didn't do anything bad, but it didn't let us do anything useful either. Right? So this says that should have at least been 7 or higher. Okay, once you pick that to be 7 or higher, you can pick your read quorum to be 12 minus whatever that is. Okay, plus 1. Yes.
I didn't understand the logic behind picking exactly more than half end of the.
Okay. The question is, why do you need to have at least half? That's your question, right? Okay. So now, if you do not, so let's say you pick them arbitrarily. Okay. Let's say you say read quorum is 2 and write quorum is 2. You pick that. Okay. Can you guarantee that if I pick 2 servers at random and they happen to just agree on the write or the version number that is guaranteed to be the most recent one? You cannot, right? So I'm just making a simple example thing. Of those 12, you say to write, pick any 2 servers and write. To read, pick any 2 servers and read. Okay? So if I write to those 2 servers, I and j, and I read from A and B, just if A and B happen to agree, that still doesn't guarantee those are the most recent version, because those could be 2 old writes and the version number happen to match. What we want is a property where if you read from the read quorum and the version number matches, it's an absolute guarantee that that's the most recent version. There's nothing more to check. Okay? To do that, you have to have a strict majority, first of all. Okay. Second is, having picked that strict majority, you want to still pick the read quorum so that there is no way to pick servers where there's at least one server from the write quorum has to be part of the read quorum. That is why you have those 2 adding to be greater than n. Okay. And so if this is not a strict majority, you will actually have problems. Okay. Because the example I just gave you where you just pick 2 or something like that might give you an error. So you want those 2 properties. That's the intuition. There's a proof for it as well. Okay. Okay, last example there, where your write quorum is actually the entire set. So all writes actually go to all the servers. Okay, that's the simplest case we had started with. Okay, in this case, the read quorum has to be only 1. There is no need to check with any other server. You can pick any server you want. Okay, read from that server. You are guaranteed to get the most recent file, because the write quorum ensures that every server actually sees the write. Okay, so this is also called read one, write all. Okay, so you always write to all. If you write to all, you only need to read from one. Okay, and you can pick any way you want. Okay, you can pick the read or write quorum. So long as those properties, 2 properties are satisfied, this is going to work just fine. Okay, so these are called quorum-based write protocol. These allow you to replicate your writes and then read and yet have guarantees. And they work well in large distributed systems where data is replicated across lots of nodes and so on. Is that clear? Yes, question?
Since we satisfy the property that nr plus n is greater than n, why not just read the version number which has the greatest commit number, or like the version number, the file with the greatest version?
Okay, so I didn't follow your question. So you are saying why not find the most recent version number and return that file?
Since it writes to one of those reads, like since we have this property that when we read from 3 machines, at least one machine will have like the most updated version.
Okay, so you are simply asking a different question, which is, say I just pick a read quorum, and from that read quorum I just pick the one which has the most recent version and do something, right? I suppose you could do that. Here you just want them to agree that if it's identical, because this has to work even when there are failures and so on. So there are a lot more dynamics than what is shown in this picture. Okay. Any other questions here? Yeah. Okay. So that's the remote write protocol, local write protocols, and replicated write protocol. So we went through 3 different techniques. I'm going to tell you a little bit about replica management and content distribution before we switch gears and talk about fault tolerant systems. Okay, some of what I'm going to talk about here is going to be relevant in the context of the World Wide Web. Okay, so here we are talking about the problem of replica placement. Okay, in all of these previous slides, we did not make any assumption on where the replicas are located. We just said you replicate n times. We didn't say where those n servers are. Okay, now in the context of large geographically distributed systems, in addition to replicating your data, it also matters where you put your replicas. Okay? So you have to typically put replicas close to your users. That's the intuition. Because if you replicate and put the replicas far away from the user, there is still a latency that is involved in accessing your data. Okay? So you want to geographically distribute and put the replicas closer to the user. So, and we'll see when we talk about go to the web that there are many web pages that have skewed access pattern. There are lots of accesses in some countries, maybe not enough accesses to a page in other countries. So it doesn't make sense to replicate everywhere. So where you put your replicas has to depend on where the request for that file is actually going to come from. Okay. So, and we'll come back to that when we talk about this later. Okay. And then there is another issue, which is do you want to actually replicate or cache your data? Okay. Caching is a form of providing good performance through replication without actually having to put replicas. In the context of the web, you might have only a small number of web servers, but you will have lots of replicated caches which actually cache copies of the file. Okay, in that case, you still get the benefits of replication. You still have to perform cache consistency, but you may not need to pay high price of actually replicating the data. Okay, so there are these two schemes that we will talk about, whether you are going to do mirroring, which is actual replication. Mirroring is just a term that says replication, or you use proxy servers, which basically are caching or an on-demand form of replication. Okay? And last but not least, who is triggering the replication? Is it server initiated or client initiated? Okay? Server initiated says it's server's job to figure out how to place the replicas and how to replicate the data. Client initiate says that it is completely on demand. When client makes a request, that is when you decide where to put the replicas. If you suddenly start seeing more requests for a web page coming from a certain geographic region, maybe there is a news story that broke that is specific to a local region, there's more local interest there. So then maybe you dynamically put a replicate copy of that web page in that location. Okay, that's essentially client initiated replication. Server initiated says that the server actually has to decide where to put the replica. Okay. So there are many of these design choices. Are you going to do this on demand or not? Are you going to do this server initiated or client initiated? How are you going to figure out where to put your replicas and so on? So when you have these larger distributed systems, you have to think about all of these issues that come under this umbrella of replica management. This is not so much as how are you going to do reading and writing. This is the whole question of how many replicas do you have, where do you put them, is that done dynamically or statically, who is going to drive replication of individual object, is it the server or the client, is it the workload that's going to dictate it, and so on. Okay? So many of these issues, I'm just mentioning them at a very high level now, but many of these issues are very important when you talk about data replication. Okay? And rather than thinking about them more generally, it makes sense to think about them in the context of a particular system, such as the World Wide Web. And we will, okay, your question there. Is client initiated somewhat like caching? On-demand caching is a form of client initiated replication in caches. Okay? There may be other ways to also do this. Okay? So in cloud computing, for example, if there are more requests from a certain location, your system can actually put a new server there. That's not caching. It just says like this happens in many cases when you have games and things like this. So if you have online multiplayer games, the popularity of those games keeps changing over time. Suddenly there is more users from a certain location because the game became popular there. Then you go place your game servers in that location. Okay, that's basically driven by client requests. That's not caching as per se. So the techniques can be more general. They don't have to be caching specific. Okay, so what I was saying is rather than talking about those things more generally, we will talk about them in the context of content distribution, which we'll again come to when we talk about World Wide Web. Okay. Content distribution networks are essentially very large scale networks of proxy servers, okay, that massively replicate web content. So a lot of the issues that we've been talking about become relevant there. So that is the context in which we will study them, but we are going to come back to them in the next 2 or 3 lectures, which is the first subsequent chapter in the book. Okay. So I'm going to wrap up and then we'll move to fault tolerance. Okay. So essentially, replication and caching are 2 techniques that are very related to one another that we can use to improve performance. Okay. In fact, in the context of the lab, okay, in your lab 2, you have replicated the front end servers. Okay. In lab 3, you are going to add caching to that front end servers. Okay. So you will have replication and caching. If you will see, go and read the lab spec that I put out, you are going to actually have caching. You will have to implement some form of cache consistency. You will have some of the issues that I was talking about as to how you ensure cache consistency and replicate data. All of that is going to become relevant to your lab. And you will see the differences. When does replication help? When does caching help? And so on. Okay. So the biggest issue when you have replication or caching, or which also replicates data internally, is you want to ensure consistency. Last time we talked about a whole slew of consistency semantics, from strict consistency all the way down to eventual consistency. Today we were talking about implementation. Okay, we talked about 3 techniques: replicated write, local write, and quorum-based protocols. Not replicated, remote write, excuse me, local write and quorum-based, which are replicated write protocol. And depending on the system, all of them are used in one form or another. In most distributed file system, you will see remote write or local writes. And we'll come back to NFS and distributed file system. You'll see that replicated writes are used in other contexts when you want to deal with failures and so on. Okay. So let me switch gears and switch slides as well, and talk about a new chapter, okay, which is fault tolerance. Okay. So we talked about replication in 2 or so lectures. In the next 2 or so lectures, we are going to talk about fault tolerance, which is how are you going to be able to handle failures in your system. Okay. Today we are going to talk about some higher level concepts first. Then we will start talking about many different techniques for fault tolerance. Some of them actually involve replication. So we'll talk about Byzantine faults, the Byzantine general problems, talk about distributed commit, 2-phase commit, 3-phase commit. We'll talk about Paxos, okay, which is a protocol that is used often to ensure fault tolerance. Okay, and then we'll talk about failure recovery. Okay. Paxos is actually part of your lab 3 as well. Okay, but we won't talk about that today. Maybe we'll come to it next time. Okay. So let's talk about fault tolerance and as to what this means. So if you have a single machine, okay, not a distributed application, okay, it's either going to, when it's up, it functions as expected. Okay, and if there's a OS crash or some such thing, it basically stops functioning. Okay, and so in the presence of a fault, if you have a single machine system, they just don't work. In a distributed system, that need not be the case. If you designed your system well, if one or more nodes of your system fail, the other nodes can take over the task of performing whatever the failed node was doing. Okay? So your system will continue to function. Okay? Your lab 3 will make you think about this carefully, because you will have fault tolerance. One front end node will fail, and you are expected for the other node to take over all of that task. And if the first node comes back, it's going to do a recovery. So you'll implement some very simple variants of what we are going to talk about here. Okay. So in a distributed system, okay, if all nodes fail, of course, even in a distributed system, nothing can be done. But the assumption is if some subset of the nodes fail, you can continue to function. Okay. And then you want to ask, how can we recover from these partial failures, what techniques to use, and so on. Okay. Now, why is this problem important? And why is it specifically important in a distributed system? Okay, this is because if you have n components in your system or n nodes, the probability that any node fails, okay, keeps growing as the number of nodes in your system keeps growing. Okay, assuming independent failures, because the probability of a failure is the probability that any one component fails, which is 1 minus the probability of no failures. okay, which is going to be 1 minus p to the power n. Okay. And as n goes to infinity, that second term goes to 0, which means that probability trends to 1. Okay. So as you have systems with very large number of nodes, okay, failure becomes the common case, not the uncommon case. Okay. In very large clusters, for example, if you have a server cluster with 1,000 or 10,000 nodes, you have to assume that some small fraction of those nodes will actually be down at any given time, because the failure rate is such that some small number of components are going to fail. So if you assume that that's a rare case and design your system, you will actually not be getting the right results, because failures will have become a common case, not an uncommon case in the large systems. Yes, question?
So like this is just a maths of it, but what are the common cases why systems actually fail in large distributed systems?
Okay, question is why do these machines fail? Machines can fail for any number of reasons. There can be hardware faults or software fault. Those are the most two common kinds of failures. Hardware fault simply means disk failed, some electronics on your machine failed, power supply failed. Okay, so any of those things could go wrong and the machine would stop. Software fault simply means that there has been a software crash because maybe you triggered a bug in the system and then it just caused the machine to hang, or there was some memory error, okay, when there was some memory bit was read incorrectly and it caused the system to malfunction. So there can be any number of reasons your machine can hang, your machine can just fail because there are hardware faults and so on. Okay. Those are typical types of failure. Now, there are many interesting papers that actually do analysis in a large system. What are the typical kinds of failures? Okay, let's say N faults were disk failures, and M faults where motherboard failed, and there's many faults where system just crashed and some things like this. So there are analysis of that, but any of this could trigger a failure. Okay. Now, just to put this in perspective, okay, why is this important? The reason this is becoming more and more important is that we are relying on computing to do increasingly important tasks, and those tasks are actually addressing needs of normal users, not tech savvy users. Okay. If you are essentially more of a computer science student or engineering student, the fact that your machine hangs and you have to every once in a while reboot your machine is not a strange thing to you. Okay. You expect to do things like this, but ordinary users do not expect to do these things. Okay. You do not go and reboot a TV. Okay. That's not how a television is designed. Okay. So now today that's still true because you have smart TVs that essentially run Linux and whatnot, but that's not how other devices are built. You don't reboot a car. You expect it to turn on typically, unless there's a problem with the car, you expect it to turn on. Okay, but computer systems are actually buggy by design. You never actually have a piece of software that is essentially 100% bug free. Okay, that kind of design methodology does not exist. You basically say it's good enough and you ship it. Okay, and good enough means it will still have some problems that will get triggered at runtime, and then things will fail, and users don't expect that to happen. Okay, and so when you tell somebody else saying, oh, such and such thing happened, you have to reboot your machine, and some of them will say, why is it designed this way? Okay, so essentially that's a problem that now you have to increasingly face because the systems have moved mainstream. Okay. Everyone in your society depends on computing systems in some shape or form, and now reliability has become very important. If machines fail and you can't access your bank site, then you cannot actually have access to your money. So real things actually get impacted, not just I cannot play a game or some such thing. Right? So essentially what that has meant is now you have to make your computing systems more reliable. Okay. At the same time, these systems are also distributed because they serve large numbers of users. Okay, distributed systems only make the problem worse because the probability of failure is higher in a distributed system than in smaller system. Okay, and at the same time our systems are not reliable. So all put together, this has caused a lot of problems. Okay, you will see that failures of systems cause all sorts of problems. Okay, the airline system goes down, flights don't take off. Okay, and then there are lots of people who are impacted as a result. Okay, bank system goes down, people don't have access to their money, and so on and so forth. So a lot of these problems occur, and of course, there is also the issue of making these distributed systems secure, because sometimes the failures actually occur because of security attacks rather than bugs in hardware and bugs in software. Okay? So that's a completely different area of research and as well as design as to how to make the systems both secure as well as reliable. We'll see that in the case of failures, we will actually look at some aspects of both, because we will not necessarily distinguish why there is a failure. Maybe the failure is caused because there is a problem, security problem, or the failure is caused because of a bug, and there will be some protocols that can deal with either one. Okay. So the basic point is we want to build dependable system. Okay. Dependable system says that these systems will stay up for large periods of time, and dependability is actually measured in the form of a metric which says how available is your system. Okay. For what fraction of time does it stay up? Okay. And that's computed as a percentage. Okay. So now there's something called 5 nines of reliability. That 5 nines essentially says that is 99.999, so there are 5 nines. So if you have a system that's 99.999 reliable, that's a highly reliable system that says once every year you have downtime of a few seconds or less. No matter what happens, your system has to stay up for a very large fraction of the time. You can have 4 nines of reliability, which says 99.99. That still gives you a window of maybe a few hours every year and things like that. Okay? Very few systems meet 5 nines of reliability, but today that's still considered to be the gold standard for reliability. Okay? So you cannot typically guarantee anything more than that, because you can have other problems that you cannot really guarantee. Okay? So essentially, you want to have high availability, you want to have high reliability, which means it should not expect failure. You should have safety. Safety simply says if some nodes fail, it doesn't lead to cascading or catastrophic failure. Like, so if you have things like self-driving cars or an airplane that is being driven by computers or nuclear reactors, you don't want some system failures to cause catastrophic problems. Okay, would you ride a car where if the camera fails, it basically crashes? You don't want that to happen, right? Because you are putting lives at risk. Okay, so all these things actually start mattering a lot more than it has in the past. Okay, and then you have to think about how to design your systems well as a result. Okay, maintainability is another property which says that once a system fails, it should be easy to repair. Okay, so I mean that's also not an easy thing, because you have to design your system to understand what parts failed, just replace those components or fix those components and so on. Okay. So those are some basic concepts. We'll start talking about techniques as well. Okay, but there are different kinds of faults that we might have to deal with. Okay. Transient faults, there are intermittent faults, there are permanent faults. I thought there was a table on this. Okay, here. So transient fault essentially says that the fault is temporary, it comes and goes. Okay, intermittent fault says that it's intermittent, but it's present for some period of time, then it disappears. Permanent fault says the component has actually failed permanently. Okay, so faults can also come in different flavors. Okay, there's no such thing as only one type of fault, and here is a table that shows you how those faults manifest itself into system behavior. Okay, so there's something called a crash failure. It's the simplest kind of failure. Okay, a fault just causes the system to crash and stop functioning. Okay, system just stops because it just crashed. Okay. So that's actually the easiest to detect and fix, because you know that it just did not produce a result. Okay. There's something called an omission failure, which says it does not respond. It's up, the system is up, but it's not responding to requests. Okay. There's a receive omission, which says that it does not receive messages, or the send omission, which is receiving messages but not replying to messages. Okay. There's timing failure, which says that the system is up, but it's producing responses that are sufficiently slow that you cannot do anything useful. Okay, so you might go to a website, it's very, very slow. Okay, you basically, it doesn't give you any utility because you don't want to wait that long. It's a kind of a failure. Okay. Now these other kinds of failures that we'll talk about are more subtle. Okay, response failure says that the system is up, but it's producing wrong responses. Okay. This often happens if your machine is hacked. It's still up, but it may be producing garbage. You can't trust what it is doing. Okay. And so there are many kinds of those, but the most general kind of a failure is what's called arbitrary failure, also called Byzantine failure. Okay. These are the hardest kinds of failures to deal with because the system is Byzantine. It can do different things at different points in time. Sometimes it might seem that it's functioning correctly. Other times it can start producing garbage just to confuse users. So these are the hardest kinds of failures to deal with. Okay? So we'll see how to deal with most of these, but these are just examples of the types of failure models you can deal with. So when you say I want to make the system fault tolerant, you have to say fault tolerant to what? What kinds of faults do you want to deal with? If you want to deal with crash faults, they're simple. Okay? You can detect whether a process is up or down. If it's down, then you deal with it. If it's Byzantine faults, it's harder because it says that the system may be up, but now you have to actually check what responses it is producing. Are they right responses or wrong responses, and then deal with that. Not just say is the function system up or not. Okay. So I'm going to show how some of these things work using a very simple technique from designing fault tolerant circuits. Okay. So here is basically on the top a circuit that has 3 stages, A, B, and C. Okay. So each stage takes 1 bit of input. It does some computation on that bit and produces an output that is fed to the next stage, okay, which does the same thing, which is fed to the next stage. Okay, so that circuits often behave this way. You basically have a pipeline where your bits are flowing. Okay. Now, if you want to deal with a failure in that circuit, okay, you might, so if A fails, the whole circuit is going to fail, or B fails, or C fails, the whole circuit fails. Okay, because it's not going to produce an output if one of them fails. Okay. So what is shown on the second figure here is where you replicated each stage. Okay, there are 3 copies of A, 3 copies of B, 3 copies of C. Okay, and there's a voter. The voter is essentially going to take the output of the previous stage and pick the majority. Okay. So basically, if A1 fails in a Byzantine manner, it starts producing garbage. Okay, if you feed it 1 or 0, it can produce an arbitrary results. The other 2 are still functioning correctly. They will vote. You will vote on the results of the 2, and then since there's majority, you will get the right response. Okay, and then you will feed the output of the vote to the next stage, which is going to do the same thing. You'll have voter and so on. Okay. Now, if you have only 1 voter circuit, that's itself a single point of failure. So because you're trying to deal with failures of A, B, and C, but you put 1 voter here. What if that voter fails? Okay. Which is why you see that the voter itself is also replicated. You have 3 voters, so that if 1 voter fails, so the circuit may be behaving correctly, but the voting circuit may be faulty. So if that produces garbage, the other 2 still produce the right result, and then that gets corrected in the next stage. To how you will design your software systems as well. You might replicate a server and send each request to all the replicas. Those servers will produce a result. You will vote on those results. You will pick a majority. Okay? But if the voting machine is a single point of failure, it might itself get hacked, or it might itself experience some fault. So it might produce an incorrect result. So even the voter has to be replicated. You had a question there?
Shouldn't the voter also be necessarily connected? Because let's say if voter 2 goes down and
Yeah, so if voter 2 goes down, that's okay. So the question is, should the voter actually feed, are you saying the voter has to feed, each stage only takes 1 input. So you can't have multiple lines coming to an input. Input is 1 bit, right? So you can only have 1 bit as an input to any stage. So in this case, the voter takes 3 outputs and produces the majority of the 3. So if this signal is 1, 0, 0, it will produce a 0, for example. Okay, or is 1, 1, 0, it will produce a 1. And then you feed that to the next. So your question is, what if V2 fails? If V2 fails or starts producing garbage, you cannot trust B1. Okay? But V1 and V2 are producing the right result. They will feed the right input to B2 and B3. So at the next stage, whatever B2 has fed will get discarded because B1 and B3's outputs will dominate, and then the stage will still be fine.
so we're not considering very pathological cases where, let's say, 2 out of 3 fails and that kind of thing.
Okay. The question is, are we considering cases where 2 out of 3 fail? That's a good question. I should have mentioned that this circuit is designed to handle 1 failure at a time. to do one failure in every stage, okay, not just one failure across the whole thing. Okay. This is called triple modular redundancy, TMR. Okay. So to deal with one Byzantine fault, you want to do 3 times replication. Okay. And this can be generalized. If you need to actually do 2, you will need 6 or 7 of those components. Okay. So you have to decide how many concurrent faults you want to handle. So this is a one fault tolerant circuit. Okay. At any stage, at every stage, you can deal with one failure, and still it will fix itself in the next stage. Yes, question?
One failure on any one of those components, or like one failure in like only A starts failing?
Okay, question is one failure in every component. This is replicated enough that you can have A3 fail, V2, B3, V5, all failing concurrently, and still everything is fine. Because at every stage you are designed it to handle one failure in that stage. What happened in the previous stage, you don't care. Yes, if A1 and A2 fail, this circuit will not do, it will produce exactly the wrong result, because those two will vote and they might produce the wrong result. Because you can't have 2 failures per stage, you can have 1 failure per stage. Okay, so this is one fault tolerant. We'll design K fault tolerant systems where K can be chosen. If you want to do K equal to 3, then you will actually need a lot more replication than this, obviously. Okay, so, but you will see that replication is coming, or fault tolerance rather, is coming at a high cost of replication. To deal with one fault, we have to essentially put 3 times the amount of hardware at every stage. Okay, this could be a multi-tier application. Okay, this could be your HTTP server, and that's your app server, that's your database server. You are essentially doing voting at every stage, and now you can imagine you put, instead of 3 machines, you put 9 machines and then several voting machines in between. Okay, so it doesn't come for cheap. But if you want to actually deal with faults, this is what you have to do. There's a question somewhere, yes.
Are Byzantine faults just faults that you just don't understand what they are?
Okay, question is, what are Byzantine faults? We are going to come to Byzantine faults in just a moment. Essentially, a Byzantine faulty circuit is allowed to produce arbitrary responses. Okay, so think of it as a machine that has been, or a circuit that has been taken over by a smart adversary that can look at the input and do whatever it wants. It can produce the right output, the wrong output, no output. Okay, you are capable of doing anything. Okay, and you still want to survive. So there is nothing worse you can do than I will basically do something to confuse. So you have adversaries that are actively trying to defeat the fault tolerance schemes, and you still want to tolerate those kinds of faults. As opposed to crash faults, they don't produce bad output, they just produce no output upon failure. Here you can produce a bad output and in arbitrary ways. Okay? Yes?
Can you have multiple servers coordinating to create an attack like that?
Can you have multiple servers? If you have K fault tolerance where K is greater than 1, okay, those two, let's say 2 fault tolerant, and if it's Byzantine fault tolerant, those 2 servers can even collaborate. So that's why I said you can do arbitrary things to produce bad output to confuse the adversary. I mean, confuse the system. Okay, any other questions here? Okay, so that's exactly what the next slide is actually saying. So how should the processes agree on what the output should be? So we are essentially going to talk about K fault tolerant systems very soon. Where the system can survive K faults in each stage. Okay, so K faults for every stage and yet function. Okay? And if you wanted to do K faults where they were crash fault tolerant, that's straightforward, because we are assuming if the server is up, it is doing the right thing, and if it's down, it's doing nothing. It's not producing any result at all. Okay? In that case, if you want a K fault tolerant system, you just need K plus 1 servers. Because it says K servers can fail, but then the one server that's left is doing the right stuff. Okay? So in other words, let's say K was equal to 1. That means you need 2 servers to deal with a crash failure. If one fails, the other is functioning. We are just assuming that if it's up, it's producing the right results. We trust whatever the output is. Okay? That's not true if you have Byzantine faults where processes or servers continue to run even if they're faulty, and then they produce erroneous errors, random error, malicious errors. They can do whatever they want. So in this case, if you assume that you can have Byzantine faults, you cannot trust the output of any one server because it may be producing bad output. So then you need more than k plus 1, lot more than k plus 1. In fact, we'll see that you might need at least 4 times the number of servers to actually deal with that kind of faults. Okay, is that clear? So there are two kinds of failures. Crash fault tolerance is very simple. You just have to detect the fault and then make sure that some other server is producing the right result. Byzantine fault tolerance is very hard, other end of the spectrum. Okay. All right. So we'll talk about Byzantine faults for the next 20 or so minutes. First, we are going to talk about a scenario where there are the processes are actually not faulty, but the network is faulty. Okay, so you have two machines that, let's say, they're communicating with one another over a network. So we'll assume the process, we're not going to worry about processes failing at the moment, but we'll assume that the network is Byzantine faulty. So you send a message 1, the network can deliver 1, the network can deliver 0, the network can deliver nothing. It's up to the network because it's Byzantine faulty. It can behave arbitrarily depending on what's going to happen. Okay, so now what we want to do is to see if you have a 1-bit message, can the two machines agree on what that message was, because the network is doing arbitrary stuff. Okay. So, and then we can actually make this example a little easier to think about rather than thinking about networks and bits by saying, let's say you have, this is called the two-army problem. There are two armies or maybe two divisions of the same army that's waiting to attack a common enemy. Okay. So the enemy, the two army units are coordinating through a messenger. Okay. The messenger is going through hostile territory. Okay. So the messenger could be captured, okay, and maybe a enemy sends a messenger, a person masquerading as the messenger with a fake message. Okay. So you send a message and you don't know what has actually happened, because the messenger could reach successfully, could get captured, never reach, could get captured, and a fake messenger is sent with a fake message just to confuse the other unit. Okay. And the problem is, in the presence of this kind of scenario, can these two armies agree on something? Let's say they want to agree on what time to launch the attack. Okay. How would you do it? Okay. So you can say, can you actually send, so what would you normally do? You will say send the messenger. If the messenger reaches the other end, have the other end send an acknowledgement saying, I received your message. Okay. So you say, let's attack at 8 in the morning. Messenger goes there and then gets acknowledgement back saying, I delivered a message saying, let's attack at 8. Here's an acknowledgement. Okay. Now, if you get the acknowledgement back successfully, does that mean that we've reached agreement on when to attack? Okay, the answer is no, because how does the other side know that you got an acknowledgement successfully? Okay. Now maybe you'll send an acknowledgement to the acknowledgement saying, yes, I received that, you acknowledged my message. Right? So message goes back, but you have the same problem. You don't know if your acknowledgement to the ACK actually went back either, because what if that messenger got captured, never reached? Okay. So if you think about this, no matter how much you recurse, you will always have this problem where you don't know whether you actually successfully agreed on something. Okay, all we are trying to agree on is 1-bit message saying what time should we attack, but we cannot get agreement if we say that the network is Byzantine faulty. Okay, yes?
Isn't that what happens in TCP though, a three-way?
Is that what happens in TCP? No, that's not what happens in TCP.
There's like a three-way handshake that is happening in
Yes.
TCP, and then everybody knows that, yeah.
Yes, because TCP is not assuming a Byzantine faulty channel. You just send an ACK and you get an acknowledgement to the acknowledgement and just assume that that's done at that point. Okay, if you are actually assume the network of Byzantine faulty, that would not be the case. Okay, but TCP is retransmitting. You have to remember that the SYN messages are actually acknowledged and you get an acknowledgement. So once you get the acknowledgement, you think you're done. Okay, so we will not worry about TCP for the moment. Okay, but the thing is, the simple property that this is telling us is two perfect processes cannot even agree, send 1-bit message successfully if the network is Byzantine faulty. Okay? So basically communication over a faulty network is basically impossible, is in a Byzantine faulty network is impossible in this case. If you want to reach agreement, you can communicate, but you won't reach agreement. Okay? So that's one thing to keep in mind. So let's leave that case aside. Let's assume that the network is not the problem anymore, okay? But it's the army units that may be faulty. Okay? So we are going to talk about a very classic problem in distributed system called the Byzantine general problem. Okay? So in this case, we will assume that there are a set of generals that have units or divisions of the army that are trying to agree on when to attack a common enemy. But in this case, some generals are traitors. Okay? This is why this actually happened in Byzantine, the area of Byzantine long time ago, where there was a lot of plotting and there were traitors, so you don't know whom to trust, whom not to trust, and so on. Okay? So now we'll not worry about the network. We'll assume that messages can go reliably, but we do not know whom to trust and whom not to trust. Can we reach agreement when some of the generals are actually traitors? Okay? If essentially, can n generals reach agreement if there are some subset of traitors? Okay, we'll start with, let's say, one traitor and some reliable generals and see how to do it. So here is an example of how we are going to handle the Byzantine general problem. So we'll assume there are 4 generals. Okay, 1, 2, 3, and 4. Okay, and we know that 3 is Byzantine faulty. Okay? But the generals themselves don't know that, obviously. They don't know. One doesn't know that. One knows that it is not faulty. Okay? But whether 2, 3, or 4 are not faulty or not, it has no idea. Okay? But one of them may be faulty or none of them may be faulty. And this technique can handle, right now that we are going to talk about, one fault. One Byzantine fault, which is, in this case, we already know that 3 is the one that is faulty. Okay? So can we get agreement among the other 3 generals, even though 3 is going to inject arbitrary messages to confuse everyone else? Okay, so this is a recursive algorithm from Lamport, okay, and it works as follows. So we are going to basically have each general essentially broadcast what they think. Let's say in this case, you can say either let's attack at this time, or here is how many soldiers I have. Doesn't matter what you are trying to agree on. Okay, you are going to essentially send your information to everyone else. Okay, so 1 has essentially sent its message, which is labeled 1, to all the other 3. 2 has sent its message labeled 2 to the other 3, and so on. Okay, so at the end of the first round, general 1 has gotten messages 1, 2, X, and 4. X says 3 is sending garbage. Okay. We don't know what it sent, so we are just going to mark it X in this case. Of course, 1 doesn't know that 3's message is garbage yet, but we assume that 3 could send arbitrary messages. It sent X to 1, Y to 2, and Z to 4. Okay, these are variables, which means the message could be the same, it could be arbitrarily different. Maybe it will send the same message to 2, yes, different message to 3. It doesn't matter what we send. Okay. Now we will recurse. What will happen is every general will say what did it receive from everyone else in the previous round. Okay. So at the end of the second round, 1 is going to get 1, 2, Y4 from itself, or not from itself, from 2 is going to get A, B, C, D from 3, is going to get 1, 2, Z4 from 4. Okay. And 2 is going to get this, and 3 is going to get this message. Okay. So if you compare the message, you will see that 2 out of the 3 will agree on what they received. The third one, which is essentially this column and this row, will not agree. So they could be arbitrarily different, or if they're actually different, the traitor will be found out, because the other 2 will say 3 sent me 10, and this one will say 3 sent me 20. You will say, okay, now 3 is sending bad messages, because that row and column will disagree with one another. Okay. So at this point, because you have 3 people sending you what they sent, if 2 of them agree, you can find who the traitor is and have the other 2 agree on, and you agree with this other 2. Is that clear?
How did A, B, C, D,
Okay. So you're saying, so here's the intuition behind what's going on. So let's say you have, in this case, from each general's perspective, there are 3 other generals. It doesn't know whom to trust and whom not to trust. Okay. So I'm going to make this, give a very simple toy example. So let's say you have 3 friends. You don't know whether to trust one of them, but or whom to trust. Okay, not to trust one of them. So maybe 2 of them are truthful and 1 will lie to you arbitrarily. Okay, so you send them a request saying what is 1 plus 2. Okay, so two of them are going to say 3. The third one can say something whatever it wants. If it says 3, all 3 have agreed, so that's the right answer anyway. If they say 4, one of them says 4, the other 2 agree, so you know that who is lying. Okay, so that's basically what's happening when the generals are essentially getting messages from other generals. One of them will not match with the other 2. So now you figure out who that is. And so you not only found the traitor, you can eliminate its messages and have the agreement among the other 2. Okay, is that clear? So you need 2 out of 3 to agree from the fourth person's perspective. So and that has to happen at all the generals. So you need 4 processes, of which one is faulty, and then each of the other process can figure out which is the faulty process, and the other 3 will actually agree. Yes, to your question.
I was going to say that this sounds like this would be a
Okay, yes. That's actually good analogy to Byzantine general problem. You don't know whom to trust. Okay, so this protocol will handle one Byzantine fault. Okay, now if you want to have k Byzantine fault, then you actually need a lot more replication. But that should give you an idea of how these things work. Okay, so essentially you computed something, you voted by sending your message to everyone else. They all told you what they all got from everyone else, and then if there was a faulty process, you eliminated it after the second round. Okay. Now here is an example where you are repeating that same protocol, but with only 3 processes. Okay, and you will look at, if you actually do this example, you will figure out that this cannot work. Okay, if 1 out of 3 processes are Byzantine faulty, the other 2 cannot reach agreement. Okay, now going back to that example I was giving you, let's say you know that one of your 2 friends are lying. Okay, if you ask them what is 2 plus 3 and one of them says 5, the other says 6, you don't know. Well, that's not the right example, but if you ask them a question and they give you 2 replies, you don't know which of the 2 is true, because there's not a third person you trust that you can compare it with. You just know that one of them is a liar, but you don't know which of them is a liar because their answers don't agree. But if you have 3 friends and one of them is a liar, you can find out who the liar is, the other 2 are telling the truth. Okay, so that's essentially what this is saying, that no matter how many rounds you do this, you cannot actually identify. You know that something is wrong because the answers don't agree, but you don't know which answer to trust. Okay, so you can detect a fault, but you can't find the answer in this case. In the previous case, you could detect the fault and get the answer. Is that clear? So all this is saying is same example as the previous case, but now you only have 3 generals. The other 2 generals can't reach agreement because each one doesn't know which of the other 2 is lying. Okay, except the liar, which knows, but then doesn't help the others. Okay. Now the property we have is if you have m faulty processes, okay, then if m Byzantine faulty processes, then agreement is possible only if you have 3m plus 1 total processes, okay, of which 2m plus 1 actually function correctly. M are faulty. Okay, so if you want to have m fault tolerant scheme, you need 3m plus 1 replicas. Okay, which is why if m is 1, you needed 4, as we showed in the previous study. If you get 3, then you cannot do this. Okay, if you want to have 2 concurrent fault, this is going to become 7. Okay, so to handle 2 concurrent failures, you will have to replicate 7 times. You have to have 7 servers to do 1 computation. Okay, so you'll see that the cost of these Byzantine faults is very, very high. Okay, often as a result, most practical schemes are not going to use Byzantine fault tolerance because you have now 4 times your hardware cost to deal with 1 failure. Okay, imagine you want to put a distributed system, your hardware budget has become 4 times of what it was. Okay, so most systems will say we'll handle crash fault tolerance. So if you want to handle m faults, you need m plus 1. And typically you will say m is equal to 1, so you will put 2. Sometimes you might put 3, and then you will stay there. But if you really wanted to handle Byzantine faults, you will have to have a high degree of replication. Okay? Yes?
So does Byzantine faults imply that you have to send like different messages to different processes?
Okay. That's a good question. Question is, do Byzantine faults imply that you have to send different messages to different processes? It does not imply that at all. You can send the same message to all processes. You can send different messages to all processes. So if you send the same message to all processes, this row and that column might even agree, but it will still disagree with the other two. Does that make sense? It didn't make sense. Okay. So basically those variables say the messages could be anything. Okay. If you analyze the message, so in this case, one general one says this is what 2 has received at the end of the first round, this is what 3 has received, this is what 4 has received. So if you analyze it, you will find that essentially this row and this column are essentially looking fishy, because either they might, if I say what is 2 plus 3, okay, everyone else is saying it is 5, but this row and this column basically ends up being 6. Okay, so then you can figure out that that actually process is faulty because the other two are essentially agreeing, and 3 is sending garbage. That's essentially what is being done. Okay, so you can send the same message, but you can send different messages as well. You will still actually figure out that somebody is a traitor and lying in this case. Okay, so that is why those are variables. It doesn't matter what you say. That row column not matching is an indication that 3 is actually the problem here. Okay, yes?
Is the application of like this problem primarily related to replication or for other distributed system areas? Are there areas where this?
Okay, question is what is the application? So application not in replication as much as fault tolerance. So if you want true fault tolerance, so this is essentially the kind of stuff that was actually happening in here, that we wanted to ensure that anything can happen, and you want to figure out who's lying and figure out what is going on. So it is basically for fault tolerant schemes. Having said that, what I also said, which was that from a practical standpoint, this is too high a cost. So many schemes don't actually do this at all. They will just use simple replication and stop. Okay? When we come to distributed file system, we'll see that many applications simply do factor of 3 replication, whether it's HDFS, Hadoop file system, Google file system, or even Amazon. They'll replicate 3 times. So even if 2 fail, okay, they're only assuming crash fault tolerant. So there are 2 crash fault tolerant. They are not doing voting or anything like that. Okay, so they're looking at much simpler failure scenarios. If the actual Byzantine fault, none of them will actually work, but that's an acceptable trade-off that every system has made, saying this is too expensive to implement. Okay? Because not only needs replication, it actually needs voting. Because this voting is how the reason your recursive rounds is you're all voting on what everyone else has said, trying to get agreement. Okay, so it's all implicit in that approach. Yes.
Can you still achieve very high availability even without considering Byzantine fault tolerance?
Okay. Question is, can you have very high availability even without Byzantine fault tolerance? Availability is always computed with respect to some fault model. Okay. So if you say I want to deal with crash failures, and then you have replication and you get 99.99% availability, that's with respect to that fault model. Okay, something else can go wrong as well. Okay, and it's always relative to some fault model. There's only one thing fails, right? So if you replicate in 2 servers, let's say, and put the servers 5 miles apart, that's with respect to some kind of faults or disaster. If there's a massive earthquake, both servers go down, you still don't get anything, right? So always you have to think about what is the kind of fault I'm trying to tolerate, and guarantees can be given with respect to that kind of fault model. If that fault model itself does not hold, then the guarantees also don't hold. Okay? All right. So we ran out of time. Let's stop here. As I said, there'll be a extra lecture on Friday, makeup class to make up for what we missed last week. Okay, so this room 4 p.m. Friday. Okay, so let's talk then.